Hey everyone, I am Charlie Como, and this is my video lab report for the 5th lab about magnetism. To begin with, our purpose here is to observe the natural phenomena of a magnet falling through an aluminum tube. Some key physics concepts here will be the Biot-Savart law, Faraday's law, and Newton's second and third laws. We'll be conducting both a real-life and computational model, and I found that the results of my computational model say that the magnet will take 6 seconds more to completely fall than the experiment value. To begin with, this is the mathematical base that we will use to build our computational model with. Using the formula for the B field of a magnetic dipole, we can calculate the magnetic flux in the aluminum ring with this integral. Since the EMF is equivalent to the time derivative of the magnetic flux, from our ethics video, that derived expression is provided here, where we can now use that EMF in Kirchhoff's law to find the current by dividing the EMF by R. Now that we have the current, we can solve for the force on the loop from the falling magnet like this, and to break the cross product, we can multiply these terms here by the magnitude of mu hat and b hat to give us sine theta. Now, by Newton's third law, the magnetic force due to the magnet on the loop is equal in magnitude and opposite in direction to the magnetic force due to the loop onto the magnet, which allows us to construct this free body diagram and find our net force. Finally, we can use the velocity and position update formulas from Newton's second law to find the magnet's new velocity and position, and that completes all the natural phenomena for one time step. Our model will iteratively repeat this calculation as our magnet starts from rest and falls through the aluminum foil. Here are the necessary measurements needed for a model, which are the length, width, and inner radius of the aluminum foil, the magnet's magnetic dipole moment experimentally determined from the previous lab, and the magnet's mass. I used a compass to find which pole made the north needle repel, marked that as north with tape, and dropped the magnet south first, like so here, with the timer on my laptop helping me measure the time it takes for it to completely fall through, and found an average time of 1.34 seconds. For some checkpoint questions, the reason why we can't use a ferrous tube is that the magnet would simply just stick onto the tube because it is magnetically attracted and won't fall. As mentioned before, the falling magnet creates a change in magnetic flux in the foil, which creates an induced EMF in the foil that causes a current, which finally creates a magnetic force on the magnet that opposes its fall. As a result, this magnet will fall slower than that falling in free space. This is what my model looks like, all coded up in GlowScript. Note, we are approximating the aluminum foil as a series of stacked rings along the y-axis. These functions here calculate the magnetic field of the magnetic dipole and the change in flux over time using the formulas previously shown. This is where the current is calculated, and this is where the magnetic force is calculated, and this is where the velocities and positions are updated. After running it, our model predicts 7.502 seconds. I would like to note that the visualized blue rings represent clockwise flowing current and the red is counterclockwise. Since the dipole moment is in the positive y-hat direction, negative dB over dt for the rings below the bar is negative y-hat, which by Lenz's law, right-hand rule yields clockwise current. For the rings above the bar, using the same process yields negative dB dt as positive y-hat, which yields counterclockwise current. As a result, flipping the magnet's drop orientation would only switch the blue and red rings for current direction. The forces from each ring will still be applied on the magnet for the same duration of time, thus there will be no change in its fall time. Since our model's prediction is much larger than our observed value, I was able to create a more accurate model by adjusting mu to be 2.5. This suggests to me that I may have had some error in measuring mu from lab 3, which cascaded over into this lab. About the velocity time graph, the velocity seems to reach a terminal velocity, which means that at some point, the gravity and magnetic forces are equal in magnitude, resulting in the bar being in dynamic equilibrium. For some analysis questions, if the conductor's resistivity was super small, then the conductor's resistance will be super small, which would make the current super large, and the force from the wire on the magnet super large, thus making the magnet fall at a slower rate. If the holes/slots were cut into the tube, then the model would have less rings, which would mean a reduced current, which would mean a reduced force on the magnet from the current, which would make the magnet fall faster. In conclusion, since my initial results were consistent, I most likely made an error in my mu value calculation from lab 3, and needed to adjust that to match the experimental value. Overall, I'll still say that this experiment was a success because this is the last lab of the year, and I successfully deepened my understanding of magnetic flux and induced current. Thank you.